So the next part we will talk about in the rate of the energy change of the heat energy, the flux term, the heat flux term. So to explain, the heat flux term, which is dash dq over dx term, we will zoom in our 1D rod into a mini section of the rod. So we have a mini section of our rod, mini section of the rod, okay? And we have basically from here, which is the qx at distance x, then the outside will be the q, output will be the qx plus delta x, and this is delta x plus x distance. And you can assume, make an assumption that the heat transfer is only transferred through the rod. The surface is isolating, so there is no heat transfer between your rod to the outside. Okay, so the outside surface is isolating, isolated. Okay, then how we can derive our dash q over dq over partial dx. This qx t is the heat flux term, or you can say this is the heat energy flux term from left to right as we set up here, So when you have the heat flux, you can see the difference basically between the right and the left. When the x is really small, so this delta x is really small, so that is the limits. When x is really small, the difference between the outlet x plus delta x minus qx, and because this is heat flux is dq over dx, so over delta x, that is equals to dq over dx. Okay, that is the dq over dx. And because this is an active heat energy flux in the heat equation form, so there is an active sign here. And basically, you can think about in physical phenomenon is that if you have the qx plus dot q over the value of the qx plus delta x is over qx, means the right hand side is over the left hand side. That means you have net amount of the energy is leaving to the right hand side. So the net amount of energy is leaving. That results in your heat flux is a negative sign. So this is overall is a negative heat flux energy term. Okay, so it's negative here. Then the last thing, to derive our energy conservation equations into a 1D heat equations, the last thing is trying to get what is the relationship between UQ and temperature U, because the left-hand side of your energy conservation equation is that as function of temperature, U x T. But the right-hand side is the heat flux term. So we have to find a relationship between UQ and U. So now the last thing is to explore how Q, which is the heat term, depends on temperature U. Okay, And this is based on the Fourier observation, which is also the Fourier law of heat transfer. So based on the Fourier observation, what is the observation? Okay, what is the observation? So the first observation is that when there is no heat flux, that means my Q is equals to 0. When there is no heat flux, the temperature is uniform. Okay, so the no heat flux, that means my Q is equals to 0 when my temperature is constant. So my U is constant. That is the first observation from Fourier. Then the second observation is what? The second observation is that the heat flux is positive from higher temperature to lower temperature. The heat flux is positive from higher temperature to lower temperature. What is the third observation? The third observation is that the heat flux is proportional, okay, proportional to the difference of the temperature. So based on this three observations from Fourier, the Fourier made the Fourier law of heat conduction. So the Fourier law of heat conduction is that my Qxt, so the heat flux term, is equals to minus K du over dx, And let's put this equation into each terms and see whether it's validated. So when there is no heat flux, Q equals to 0, that part will be equals to 0. That means my gradients of the temperature will be equals to 0. Then the temperature has to be uniform. So it's a constant. Then the heat flux is positive. That means the Q is positive. That means the du over dx has to be negative. That means my temperature the gradient is negative, means the temperature is driving from higher to lower. So the second part is also satisfied. Then for the third part, when the heat flux is proportional to the temperature gradient with this K, is either can be as function of X, or it can be constant. Where is this K? It's the heat conductivity. Okay, so it's the heat conductivity. And after we derive here, so we see that, okay, we can have some relationship between my heat flux term as well as the temperature. Then we can rewrite our energy conservation equations into simplified 1D heat transfer equations, heat equations. Okay, so let's rewrite this.